Welcome to the video course Transmission Lines. Transmission line is a cable or specially designed structure used to carry electromagnetic waves. Simply, whether it is wired transmission or wireless transmission, in both the transmissions, electromagnetic waves that play an important role. Let us suppose a simple wire. When we apply a AC signal to the wire, then what will happen? According to the Faraday's law, there is an induced magnetic field around it, and that creates electromagnetic field around the wire. And if it is a wireless transmission line, say for example between antennas, there is a transmission in the form of electromagnetic waves. So let us say that whether it is wired or wireless, both are applications of electromagnetic waves. Broadly, transmission line can be classified into two categories. One is wired transmission, the other one is wireless transmission. Anyhow, whether it is wired or wireless, electromagnetic waves and electromagnetic fields, they are going to play a vital role. If it is a wired transmission, examples, coaxial cables, parallel line cables, and optical fiber cables, all these things are coming under the wired transmission, where a wire that carries the signal from one place to the other place. The second category is wireless transmission, where there is no wire between the receiving end and the transmitting end. In between transmitting end and the receiving end, electromagnetic waves flows or drift into the air, and that reaches to the receiving end. Examples for wireless transmissions are your cell phone to cell phone communication through tower antenna, and satellite to TV reception, and your remote control to TV. All these things are coming under the wireless transmission line. But what particularly we are going to talk in this course is wired transmission, and how these wired transmissions and what are the characteristics of these wired transmissions under this course. At this point, one can think of why do we have different types of cables. We have a parallel line cables, then why do we need coaxial cable? We have coaxial cable, then why do we need optical fiber cables? All these questions coming into the mind. There are many reasons, but I'm going to talk about two important reasons why do we need different types of cables. First one is skin effect. What does it mean, skin effect? So when we have AC signal that flowing into the wire, that AC signal that occupies the cross-sectional area of a wire. When the frequency increases from low frequency to higher frequencies, what will happen to the skin depth is nothing but when the frequency increases, automatically the occupation space of the wire that reduces. It means it almost comes to the edge of the cables. It means there are unoccupied or unused cross-sectional area in the wire when the frequency increases. So one can remove that unused space so that we can reduce the cost and the weight of the cable. So when the higher frequencies occupy only edge of the cable, then why do we need a larger cable? We can have a hollow type of transmission cables that reduces weight of the cable as well as the cost of the cable. That is the one important point which comes under the skin effect and the skin depth point of view. The other reason why do we have different cables, simply when the frequency changes, automatically the characteristics of the waveform also changes. Let us suppose two waveform, one is a radio frequency, the other one is X-ray frequencies. Both are different frequencies, and applications of radio frequency is nothing but cell phone communication, and X-rays mostly we see in the medical application. When we exchange these two, it means we are putting radio waves into medical field and X-rays into radio wave communication. Then what will happen? And we know that getting too much of exposure to the X-rays will cause damage to the human cells, not only human cells but also plants and animals. It will create a lot of problems. So X-rays are nothing but a hazardous waveform to the human and also for the environment. So we cannot put that into the radio communication, because when we use X-rays in the radio communication, we always getting exposure into the X-rays. So that is really hazardous to the human race as well as plants and animals. So we cannot use that over here. Radio waves will not penetrate too much into the body like what X-rays does, because X-rays high energies, they penetrate into the obstacles, but whereas in the radio wave frequencies, they will not penetrate too much into the obstacles. Either they will get reflected or refracted from the objects. So we cannot use that radio waves in the X-ray wave applications. Similarly, we cannot use X-rays in the radio wave applications. For example, X-rays can penetrate too much into the obstacles, whereas radio waves cannot penetrate too much into the obstacles. That is the reason, because when the frequency changes from radio wave to X-rays, then the properties, the characteristics of the waveform is nothing but penetrating higher in the X-rays, whereas less in the radio waves. And moreover, if you take a visible spectrum from 400 nanometer to 700 nanometer, in that range only we can see the things. So that characteristics coming under the 400 nanometer to 700 nanometer. It is nothing but a wavelength. We'll talk electromagnetic spectrum and the wavelength frequency separately. But as of now, so the frequency changes, automatically the properties, the characteristics of the waveform also changes. And the best known example what we discussed is radio waves and the X-ray waves. So let me conclude in this way that a same medium cannot be used for all the frequencies. The reason is one is skin effect, and the second important reason what I said is when the frequency changes, automatically the characteristics or the properties of the waveform changes. So one medium is not suitable for all the frequencies. So because of these reasons, we have different types of cables, different types of medium like waveguides, transmission lines. All these are used for the particular applications of electromagnetic waves. Okay, and we'll talk electromagnetic spectrum separately in the upcoming lectures. And what I'm going to cover in this video series is about transmission lines, and I've already given Smith chart videos in my playlist. You can watch that also. But along with the transmission line, we are going to end with the Smith chart. And what is the difference between electronics and electrical students in a transmission line point of view? Electronic students, they always study about these type of cables, like what I mentioned, coaxial cables, fiber optic cables, twisted pair, all these things, will be studied in the electronics course. But in electrical, they study about the power lines, which transmits or carries the electrical signal to the homes or the factory from the transformer side or from the generating side. So this is the basic fundamental difference between electronics and the electrical cables. The other difference is electronics, they study about low power but high frequency signals. And the other one is electrical, they study high power but low frequency signal. And we know that home appliances get around 50 hertz, but whereas in the electronics, we study from kilohertz to gigahertz range of frequencies, but they use only less power, right? So less power but high frequency for electronics, and high power but less frequency for electrical. This is the fundamental difference about cables in the electrical and the electronics department. And the remaining thing we'll talk about in the upcoming lectures.